Hello. Okay, so I'm back to do some problem sets. I'm going to start with a question that I've had for a long time now. Way back in lesson 3.2 it was, I believe. No, 3.1 even, a while ago. We were taught about the idea that we could go from image to kernel, and kernel to image. What I mean by this is there's an example problem. Express the image of matrix A as the kernel of a matrix B. Now, to convert from image to kernel, I believe I've already showed you that in a past video. To go from kernel to image, it's a lot simpler, but to go from image to kernel, it was a little more confusing, and Dr. Prudhomme and I talked about it a lot, and this is kind of what we came up with. So there's this problem in the book. You see this matrix. So it gives you this matrix, right? From there, the book points out that we can convert this into a systems of equations, x1 plus x2 plus x3 plus 6x4 equals y1. X1 plus 2x2 plus 3x3 is 4x4 equals y2. X1 plus 3x2 plus 5x3 plus 2x4 equals y3. And finally, x1 plus 4x2 plus 7x3 equals y4. Okay. So then you reduce your rows. I'm going to clear all of this. And you end up with x1 minus x3 plus 8x4 equals 4y3 minus 3y4. And you've got x2 plus 2x3 minus 2x4, which equals negative y3 plus y4. And then finally, you've got 0 equals y1 minus 3 y3 plus 2y4. And finally, 0 equals y2 minus 2y3 plus y4. All right. So what do you do for this? So what you're trying to figure out is for which vectors y is this system consistent? And that is how you express the image as the kernel of the kernel of a 2x4 matrix B. Well, to do this, it's actually pretty simple because you use these zeros to your advantage. So you can say that y1 equals -3y3 plus 2y4 and y2 equals -2y3 plus y4. And that's how you can then say -3y1 plus 2y4 -2y3 plus y4, y3, y4. And finally, what we always do with kernel, you split this apart and you say that the kernel is the span of -3, -2, 1, 0, comma, 2, 1, 0, 1. And that's your kernel. So that's how you do that. And I just want to clarify that. That was from a long time ago. But let's see. The next things I want to talk about is some, oh yes, if we move on to 3.4. I'm going to go ahead and show you some of these column by column things that I talked about before. So clarifying what I mean by column. So I'm going to flip to 3.4 right now. I'm going to pick a random example. They're all really similar in the beginning. All right, so it says in exercises 19 through 24, find the matrix B of the linear transformation T of X equals AX with respect to the basis B equals V1, V2. For practice, solve this problem in 3 ways. Use the formula B equals S inverse AS, use a commutative diagram, and construct B column by column. I'm going to focus on column by column, and then maybe I'll get to the other ones. Start with A equals 0, 1, 1, 0. V1 is 1, 1. V2 is 1, -1. Okay. So we have A and we want to get to some B, right? Well, let's see. I'm sorry. I'm just having to look to make sure that I'm doing this correctly. Yes. Okay. All right. In this case, okay, I'm going to make a list of what we do know and what we don't know. So of course we know our 2 bases, right? And we know our A, and what we want to get to, let's see, we can think about it. Maybe we've got A, we don't have S or B. And what B really is this. Okay, so I think the easiest thing to do is to apply the transformations first. So if we do T of V1, we end up with 0, 1, 1, 0, becomes 1, 1. All right, so what we end up with is 1, 1. So in other words, T of V1 equals V1. And let's look at what T of V2 is. So T of V2, in this case, we've got 1, 0, 0, 1. Nope, that's not correct. I got it mixed up. It is 0, 1, 1, 0. And then you multiply that times 1, negative 1. And surprise, surprise. This time you get negative 1, 1. So in other words, you get negative V2. So I believe what you would do from here, right? We're looking at what the coordinates are of this, right? And so in this case, for V1, it would be 1, 0. And for V2, it would be negative 1, 0, right? Sorry, it should be 0, negative 1. So, yes. Let me see. Let me just make sure that that's correct. Okay. So if we draw that out, we end up with 1, 0, 0, negative 1. Is when we have something like this, where we know that T of X is equal to V2 times X. This emulates the problem in the book that we had. We're assuming that these are like perpendicular. This is the case that's important to realize. So if we plug everything in, right, we've got 3 bases. We've got V1, V2, V3, right? And well, let's figure this out. If we plug in T of V1, we have V2 times V1. That gives us V3. If we have T of V2, that's V2 times V2. That's going to be 0. And if we have T of V3, that's V3 times V2. That's going to give us V1. So we construct a B matrix from that. 0, 0, 1, right? So for T of V1, it should be V3, 0, 0, 0, T of V2, 0, 1, 0, 0, T of V3, V1. And that's our B matrix. So it's really quite simple. It shouldn't be too difficult. Now, our next, let's see. The next problem that I'll take us through, I think, is looking at if two matrices are similar. Let me clear all of these. And then I think I'll stop from there. So, is matrix 2, 0, 0, 3 similar to matrix 2, 1, 0, 3? So again, this is a situation, and I'll pick a different color. We've got an S, right? And we're imagining that we've got, say, X, Y, Z, T. So let's multiply 2, 0, 0, 3. So if we were to do that, You have to think about it like this, like we're used to. And it would yield this matrix, 2x let's see, 2x 3z 2y 3t. And that has to be equal to this, where we do x, y, z, t, multiplied times our other matrix, 2, 1, 0, 3. Right? So that would give us 2x. It would then give us 2z, yes, 2z. Then x plus 3y. And then, of course, let's see, z plus 3t. Right, and these two things would have to equal each other. And if you flip back into the book, to the part that shows this, you would then simplify all these equations down. And let's see, how would we do this? The book didn't really clarify how exactly you're supposed to go about doing that. Let's see. I believe if we look at what they did in the other example, let's see. I think potentially you subtract, right? So this would cancel out. And then I believe that you would subtract 2y minus x. Well, no, but that wouldn't work. Let's see. I might have to come back to this question and talk about how exactly they mean to simplify. Although, let's see, I'll look at it for a minute and see if I can come up with anything. I'm sure it's quite simple. I just haven't thought of it. Let's see. No, I think that might be correct. Okay, so these two cancel out. Then you have, let's say, 0x plus 2y minus x plus 3y. So it's going to give you negative x, negative y. And then, right, so you end up with 0, negative x, negative y. And then 3z minus 2z is z. And then 3t minus 2 plus 3t. Right? And so that would give you negative 2. Okay, so your answer to this would be that these two are similar as long as you have an S matrix where, let's see, y is equal to negative x minus y, and t is equal to negative 2. Yes. Okay. That, I believe, makes sense. I don't know. I think I'm going to give an update on this one because I'm not quite exactly sure how the book wants you to simplify. but I will definitely get back on that once I've had a chance to talk to Dr. Prudham. One problem I'm not going to do today is one that's talking about reflections. Because I'll get to it next time, but just a quick little preview. It'll have to do with being given a line of reflection and then having to sort of figure out that matrix A, and from there having to work things around to get to some matrix B. So if you're curious about that, you can start thinking about that on your own, but that's what's coming next. So thank you guys so much. I know that this problem set was kind of all over. It was some stuff from 3.1, some stuff from 3.4, but hopefully it was helpful. Thank you guys so much.